Here I am. Good morning, folks. Thanks for your patience, just getting myself set up. Thanks for joining me live this morning. I wonder if we're ready. I think we are. Good morning, everybody. Welcome back to COMP2300, our lecture on interrupts, part 2 of the interrupts and asynchronism week. It's interrupts week. I need to have a dub siren or something, wah, 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 to get some epic horn blasts up here in COMP2300 stream. Maybe we'll get one for operating systems week. Get some kind of siren going. I want to move right into the lecture in a minute. I will mention a few things which have been moving around my head that are on my mind. I'm just going to head to the admin time page. Folks, you need to look at the assignment 2 page if you haven't seen it already. If you remember, assignment 2 is all about these guys, digital pets. You are going to make your own digital pet in COMP2300. The reason I'm pushing it again today is to make sure that you don't forget that you need to have a design proposal ready by the time your lab starts in week 9. We haven't quite got the assignment template out. It should be out today. We'll make sure that happens for you. And then you can start writing your design proposal, or if you've already written it somewhere else, just copy it into your design proposal template. You need to fork, clone, and write your design proposal of the assignment template before your lab next week. You can do it. It's not that much work. It's just basically a task set for you to read the assignment and think about it. We're not expecting deep discussion here. Where are we up to? I think, I managed to hit exactly halfway through. We're halfway through this mega lecture. We're halfway there. Whoa! Dog elected mayor. Week 8, part 2, asynchronism. Where we left you last week. I need my pen. And I need to make sure I'm zoomed in the right amount. Pen. Turning on the Bluetooth pen. Zooming into 170. For some reason, you need to be zoomed in 2/3 because I want to be able to use the whole screen. Oh. What? Why is it doing that? That's not right. Oh, that's better. Okay. Where were we? We had this concept that if this is your code, this is the stack, and this is a handler for an interrupt. When an interrupt occurs in your code, the PC value starts pointing here in your code, and when the interrupt happens, the first thing it does is automatically save all of the important stuff which you are using in your program. The PC, the SP location, the link register, all of the caller save registers, all get saved on the stack automatically. Auto save, and your PC ends up back in here. Now. Someone asked on the forum yesterday, wow, if I can suddenly change into a different part of my code during an interrupt, maybe there'd be some way to kind of run 2 programs at once, right? So that student was just having like an amazing galaxy brain moment, and I just wanted to thank them for asking such a great question, because it's true. This lets us basically change to a different program. And that's going to be the theme of today's lecture. How can we change to a different program with interrupts? And what would that mean? What are the implications of that? Because there are some. And in fact, thankfully, you have a whole course dedicated to the implications coming up next semester, which is COMP2310. Systems, Networks, and Concurrency. Is that what it's called? I've forgotten the title of COMP2300. So you will learn a lot about the consequences of this in that course, but we're going to start today, again, being very practical, being very low level. What are the low level ways that we can do this? And what does the hardware on our microbit give us, which allows us to do this well? Yes. Someone's asking preemptive questions. Well, we haven't learned how to do preemption yet, so I'm not going to talk about that. I'm going to, for simplicity's sake, I'm going to delete the word asynchronism right now. And I'm going to replace it with this, running 2 programs at the same time. Running 2 programs. I don't want to live in a world of highfalutin technical terms when we have a perfectly good intuitive understanding of what we mean. I want to run 2 programs at the same time. How am I going to do it? That's the point of this lecture. Is this parallel computing? That's a good question. You can tell me that at the end. Where were we? So we just learned, I just have the document I just drew. My scribble thing was just in a picture here. How silly am I? We've just learned that an interrupt can stop our program at any time and run different code in the handler. Returning from the handler puts our program back just the way it was before the interrupt. Everything is fine. Everything is happy. The code that was interrupted away from, it doesn't even know. It's like, you know, what's that Pokemon that just is always confused? Psyduck. Psyduck used confusion. This code doesn't even know what happened. It's a duck. Is this a duck? That's kind of a Psyduck. Okay. So the original code you're running doesn't know that it's been put on the shelf for a while, stuck on the stack, and the handler's been running. So what I want to just point out is that this stuff on the stack, this is kind of or this stuff that the interrupt saved automatically, that can be sometimes called our context of execution. It's all of the information which defines what a program running is, right? It's where it's up to in the program, what its registers are, what its stack pointer is, what its link register is. If you have that stuff, you can restore a program exactly the way it was, as long as the memory and everything is still in the same state. Well, there's a great discussion in the chat. My head's blocking the stack. Sorry about that. I do have a left-hand side version of my head. I'm not sure if that's better. I'll put it on left-hand side for a while. Okay, back to the analogy. So your microbit is a starship. Remember that. This was critical assumed knowledge. Every starship has a captain. That's your program. PC, or your program is running the starship. And he's got his context of execution, R0 to R3, all part of who Jean-Luc Picard is. And then you've got your sensors, you know, this is GPIO, Beverly Crusher is Systick, and data is, I don't know, RNG, and Wesley is something else. What's an annoying one? Deep Star Trek. I'm very zoomed in now. Oh, come on. I'm not going to let this stand. Am I too zoomed in, or is that seems normal to me? I'll make myself small. I'll travel around the screen. And back. Okay, no more fun today because we have to go on our important topic of learning how to run 2 programs at once. Okay, every starship has a captain, that's your program. And an interrupt occurs, right? The GPIO interrupt has fires saying, Captain, look, there's something. The slides are zoomed in. They're supposed to be zoomed in. Oh, are they? Ah. My whole Star Trek bit has been ruined. And I blame whoever it was who said I was covering the stack. If you hadn't said that, everything would have been fine. That's okay, I forgive you. Cool. Back to streaming full screen. I'll have to do the whole thing again. Your program is a starship. Your microbit is a starship. Every starship has a captain. That's your program. Your program has its context. William Riker's GPIO. Council Troy's Systick. They can interrupt the captain if something important happens. GPIO has just made an interrupt. Captain, look, something to look at. Interrupted. Then the program is going to restore, and when the program restores, Dr. Beverly Crusher is in charge of the ship. So a new captain has entered the ring. And she's got her own context of execution, LR, PC, SP, R0, R3, etc. Her own memory stuff going on. And she's running the ship now, and she's got a different interrupt controller. So this is what we're talking about. This is a context switch, a switch between two contexts of execution. So the Enterprise can have one captain, program 1, or program 2. Oops. And our interrupt is going to either return us back to program 1 or return us to program 2. So we can use an interrupt to switch between contexts by switching out all of those context of its execution stuff, which is put onto the stack. And in fact, you can do it more simply than you might think. It is actually not that complicated to do this. You need to do a bit of setup, but you'll actually be able to do it in your week 12 lab. So wait a minute, can we now run two programs? We kind of can, folks. We can run two programs at once. Wild stuff. Context switching. Here's the big idea. We're going to have two or more main programs or different captains, and we're going to use interrupts to swap in between them. So what is the context? I was just talking about this. It's the set of information that needs to be saved for a program to start up again after an interruption. And in some sense, you can see that it's this stuff here. The program counter, where the program is up to, the flags, the values in the registers. If all of those things are restored the way they were when a program restarts, and everything in memory was the same as it was, your program's not even going to know that it was ever paused. It will have no way of knowing until later on I tell you that it might have some way of knowing. Yeah, context. The set of information that needs to be saved for a program to start up again. Context switching is switching in between two programs such that when they can restart at different times and not even know that they've been restarted. So someone asked before about whether this was parallel computing. Well, not really, because we're not doing there's not two CPUs running programs together. We just have one CPU with two programs. So sometimes it's program 1 and sometimes it's program 2. Someone's just asked, are we changing the information on the stack, or are we explicitly having two main programs? Just maybe pause your thinking process to see what I'm going to do to show you how this might work. There are many ways that you could do this. Once you have the idea that you can put a program on hold and freeze its state, take its context and somehow save it, there's lots of different ways that you could implement this. But the way I'm going to show you is this. In fact, we're going to have two separate programs in memory. This is going to be code 1 for program 1, code 2 for program 2. This program is running at the moment. We've only got one CPU, so the PC, a register, is pointing to a location in program 1. SP is a stack which is pointing to a location in program 2. But we've also got another stack. So in memory, there's going to be a different stack, which is the stack belonging to program 2. This is program 2 here. And this is program 1. I think now I need to move my head back to the right-hand side. And somewhere else in memory, visible to something is going to be a list of all of the programs that are available. And it will have particularly important information, which is what the stack pointer is up to in that second program. Okay, so far so good. An interrupt occurs, step 2. Okay, so all of this stuff has we're in the dispatcher now, or the interrupt handler. We're going to call that the dispatcher. An interrupt has happened, we're in the dispatcher. All of our context here has gotten pushed onto the stack. Someone's asking me to clarify what PCB is. I'll clarify that in a minute. We're going to go through these slides maybe twice, just to make sure we get the idea. Pushed all of the context onto the stack. We're in the handler. And now we're going to swap to the new context. So in the previous step, SP was the stack pointer that was pointing to the stack for program 1. And now I'm going to store that in memory. The handler is going to do that work, store it in memory, and it's going to restore the stack pointer from program 2 onto this stack. Now, and this is the clever bit, when we return from the dispatcher, which is an interrupt handler, when we return from the dispatcher, which is an interrupt handler, it automatically pops off the context from the stack for program 2 instead of the stack for program 1. So now PC has been restored from program 2, not from program 1. So program 1 is frozen, and program 2 is running. Happy times. Let's go through that again in a second. So I've got a few bits of information here that you will have never seen before. Special LR to run on program 2. I'll get through these questions in a minute. Questions in order. PCB. PCB. PCB is going to stand for Process Control Block. It's a word that you would use in an operating system's context. Someone's reacted to something. Oh, my tutors are laughing at my slides. Process control block. So I've used a sort of high-level technical term which is used within operating systems, but basically we're going to need to have some kind of data structure to remember what programs I'm running and where their stacks are. And the bit of my program which is going to be able to access that data structure is going to be the dispatcher, my special interrupt handler for directing the CPU towards different programs. So that's what PCB stands for. And PID here is going to be something like process ID. I just put in a really process identity or identification. I put in a very simple kind of program control block there. We'll look at a more complicated version of this in the operating systems week, because this is your start to understanding what an operating system can do for you, a multitasking operating system. Next question. Does the information on the stack automatically refer from the stack, or do we have to pop it? It was a mix. I'm possibly possibly I don't have everything exactly right. Here's the popping stage. I think this stuff, call E saved. Oh, I'll go get my package. Sorry, be back in a second. You're going to like this. It's live package opening as well, unboxing show, as well as the asynchronism and multitasking show. The question was, which things get popped off the stack automatically and which things have to be done manually. These bits, the call E save and local variables, that was like the R4 to R11, not LR. Call E save variables were going to be restored by the dispatcher, so I think that's why I colored it orange. An interrupt occurred indeed. And these things, they're automatically, hopefully you can see that, the green ones are automatically restored by the interrupt controller. Automatic. But essentially we would just have to make sure that our SP is changed. That's almost the only thing we have to do. It seems wild, but if you have a program which is going to say pop, R4 to R11 and then BXLR, as long as your stack is pointing to the right place, this is just going to take the last, R4, 5, 6, 7, 8, 9, 10, 11, the last 8 words off the stack and put them in those registers. And BXLR will return from the interrupt. The LR will still have that special value, but that special value just says to the CPU, oh, we're returning from an interrupt. Please pop off everything you found from the stack and put it back where it was. And because we've changed our stack, it's like we've taken our computer, taken its brain out and put a new brain in and then just pressed go again. So the stack is really where all of the information was stored. So if we only change SP, point to a new stack, instead of pointing to our old stack, that's the same as changing our computer's whole brain. The more you think about it, the wilder it is. I'll give it a second to sink in. How do we set up the stack for the special LR to run program 2? We don't have to do anything special because the stack, both of these stacks have been set up by an interrupt occurring and the interrupt controller pushing all of the context on to the stack, and then the dispatcher pushing a little bit more context onto the stack. And so we don't have to do anything different. As long as SP has been changed, we're all good. I'm going to go to this slide and you can have a think. Would a program notice if it's been switched out and back? And could anything go wrong here? Someone suggested something which could actually go wrong already. It was a bit tricky to get this. This is something which we're going to get to have a play with in your labs. Ooh. Original Tamagotchi. It's not an original one. It's a re-release of the original idea from Bandai. So that means I've got 2 proper Tamagotchis. I only had a really terrible AliExpress budget version digital pet. But now we can play with the original ones, which are actually pretty fun. I've got another R2-D2 one, which is pretty cool. So I'm still waiting for any ideas about how a program might notice if it's been switched out and if anything could go wrong. So there's been one really good suggestion of things that could go wrong. Stacks could intersect. Did anything else go wrong? I'll go get you can think of something that could go wrong, and I'll go get the R2-D2 Tamagotchi too. This one's tiny. Makes little R2-D2 sounds. There's got to be someone there who can think of something that could go wrong. Wow, very clever. Someone's put a really good idea there. Memory could change in between. Memory could change. Good idea. Yeah, so this is there's a few good ideas here. Someone said maybe if you pushed but don't pop inside the handler, the values might get messed up. So I think we're going to assume that my program is working perfectly. So the dispatcher is perfect, this program is getting perfectly stored, and this program is getting perfectly restored or unfrozen every time the dispatcher switches them over. But you folks have pointed to, and I guess I'm going to also assume that the stacks can't overflow. Imagine I've got heaps of memory and it's just not likely to happen, and the handler has some way of preventing it from happening. But we're not going to worry about that for now. But we do have one very important thing, which is that this is not everything that's going on in our program. All through COMP2300, I've been saying, don't always store data in registers. Use memory. Use memory. So all the way along through our program, bubbling underneath of everything, there's this whole bunch of memory. Whoops. If I go off the screen, my my pen stops working well. Memory, and that's going to be 0x2000 up to it's 3FFFFFF. Nominally, it's not full, but there's a lot of space there. But it's the same memory that everyone can access. So supposing this program, just when it had been frozen, this program was in the middle of doing something with a particular memory address. And then this program gets unfrozen and is like, oh, okay, I'm just going to start messing with this memory address because I can't imagine anyone else would be using that. And then when this one gets frozen and we go back to this one, it's not even going to know that the memory address it was in the middle of using has been messed up by another program. Or is it? Or how can it know? So this is a core problem. The core problem of any kind of multi-computing, multitasking, parallel computing, multi-computing, task switching, context switching is shared resources. How do we manage resources that are shared? Is it possible to create a safe zone where no interrupts can happen within the code? Yeah, that's an interesting idea, a safe zone where no interrupts can happen. I guess it is possible to do that, but first of all, it's possible for some interrupts. You can definitely change the priority of some interrupts so that they're low. You can ignore some interrupts. There are some interrupts that can't be ignored. So it's not possible to make a truly safe zone, but it would be maybe possible for a program to have a safe zone from some interrupts. And I guess the question is whether it's a good idea. And I will say that right now it's probably not a good idea, because if you did that, if you had a system where you did want to have multitasking and a program can say, I don't want to give up control, then everyone does that all the time, and then your operating system doesn't work anymore. So there are some, we'll talk about this more in the operating systems lecture, but there is a property of an operating system that it would be preemptive or non-preemptive. So if it's preemptive, then the operating system is allowed to boot or kick a program off the CPU and run another one whenever it wants. Non-preemptive, the program would have to yield control back to the other task. The non-preemptive version turned out to be a bad idea. So someone has just had another great thought, which is it possible for an interrupt to trigger in the middle of an instruction actually running? And the answer is no. It can't. An interrupt can't happen in the middle of an instruction running. That instruction has already been decoded, fetched, decoded, and it's in the process of executing. So many questions now. What if you've set half the LEDs and then a button is pressed? You might want the interrupt to happen after the full image is loaded. Oh, I didn't know that. Nick is telling me some truths from the tutors. If Nick tells you something, I would believe him because he knows a lot. So I'll go back to the first question. What if you set half the LEDs, then a button is pressed? Wouldn't you want it so the interrupt happens after the full image is loaded? Maybe different program designs might have different requirements there. So it's open for that kind of interrupt, a like interaction interrupt, maybe that would be a lower priority. But if there was an interrupt from the operating system kicking one task out and bringing another one in, I think that would be more of a high priority interrupt that we would allow to happen. In practice, if you're writing a program for a big computer with a big screen, you're not directly adjusting LEDs on your display. You're constructing a picture of the screen in memory, and then it's getting automatically put on the display by the graphics card. So there's kind of separate things going on in your computer to deal with a display as opposed to your regular processing, so that when things are interrupted, bad stuff doesn't happen. We need to find a way to store the memory we were working on, just the memory we're looking at though. I think there's folks running down a line of thought here. So just take this idea for a walk. I'm speaking directly to Nick the tutor here. The litter, can you get interrupted in the middle of a load? And how does it know to keep trying the load when you come back? I'm just putting an idea out into the world and hoping my tutor answers me. Anyway, we'll get back to that litter being interrupted idea another time. So shared data, and this is where we get to this running. I'm going to delete these words, they're too hard to understand. Running two programs at the same time with shared resources. Two programs, shared resources. Separate bits of memory allocated for each program. I know, but I want shared resources to be allowed. Sometimes it's of course you will want some separate bits of memory for each program, particularly local variables, right? Have local scope when you're programming. But you will always want some kind of shared data. Otherwise, what's the point of having these multiple programs? Even on your big computer, your hard drive has multiple files that you want different programs to be able to access. You can either open a Java file in VS Code, or you can open it into IntelliJ. You can open it in both programs at the same time, and they're still happy, right? So there's a shared resource, and there's some way of negotiating how that works. In the old days, a lot of this stuff was worked out in the 60s. They would always refer to things like a printer. So there'd be a lot of computers, a lot of programs running on these computers, but there'd only be one thing that can print out the output from those programs. So that would be the shared resource that had to be organized. Store all the memory on RAM and restore it after you've come back from the interrupt. But the RAM can be addressed by the other program too. Okay, let's just start to we'll get ourselves into trouble and then we'll try to get ourselves out of it. So imagine these are three separate programs running at the same time. And we've got one single global variable G. What is the value of G at the end of these programs? You tell me. What's the value of G? So this program here is going to run G, set G equal to 1, and then set G equal to G plus G, so now G is 2. Okay, and then this program is going to set G to 2, and then G plus G, so G is 4. And this one will set G to 3, so G equals G plus G, so G is 6. Is that correct? G equals 6. 2, 4, or 6. All right. Let me put it this way. This program sets G equal to 1. Okay, context switch. Bam. This program sets G equal to 2. G is now 2. Context switch. Bam. This program sets G equal to 3. G is now 3. Context switch. Back to the first one. G equals G plus 3. That G is now 6. Context switch. G equals G plus G. G is now 12. Context switch. G equals G plus 3. G is now 24. G equals 24. I feel like everyone's brains just melted at the implications of this. Whoa, yeah, seriously folks, if you have two lines of code, line 1, line 2, there could be a context switch in between any of these two lines. You have no idea. On your big computer, when you are writing Java, you have no idea if there's going to be a context switch in between two lines of code. Okay, Nick was talking about LD load multiple decrement before. So if you do LDM, they get decoded into separate letters. And similarly with push, right? If you're pushing R0 to R4, that's going to be a whole bunch of stores separate. Anyway, I've just blown everyone's brain with this idea that context switches can happen at any time. We have no guarantees, particularly not in my kind of context-free example. I'm just giving examples about abstract computing and giving you no information about what the operating system is or what might be happening. I'm just saying there are three things at the same time, and we have no idea in what... We know that line 2 of each one will happen after line 1 has happened, but we don't know what has happened in between them. So it could be as low as 2. I think it could be as high as 24, and it could be almost everything in between. I think it could be as high as 24. There might be other options. Here's another one. This is the same thing in assembly. And I'm not going to ask you to go through this in great detail, but now can you see a simple program in Python or Java turns into a lot of lines of assembly, and there could be a context switch in between any of these lines. There could be a context switch in between any of them. So you have no idea. This is why we have a whole course for you next semester about how to deal with this stuff. Don't they pop the original value of G? No, there's a question about when to switch programs. That's a very important question. It's a topic called scheduling, and we'll look at that in the operating systems lecture. You do it on a timer interrupt probably. What I want to say here is that these programs we've got a really unfortunate thing that can happen here, which is that we don't even know if this is going to happen at the same time. What does that look like in this program? G equals G plus G is this. So this is get G, that puts G into R2. This is G equals G plus G. And this is also it, where we actually store it back. So we've got these three important instructions that are taking G out of memory, storing it somewhere and putting it, or adjusting it and putting it back. So far, so good. One of these programs could think it's been updated G. It could have gotten to this stage, and then it switches back in to here, and then we just write straight over that data. So the G there is going to be just completely overwritten. We're not even loading it. So the store that this program did gets ignored. That's now we're starting to see that we're not just going to get the wrong answer, we're just going to start to ignore data. I'll show you more in a minute, but here's the intuitive way to understand this. This is a classic concurrent programming example, the too much milk problem. So it's a university student example, so you should be able to understand it. There are two roommates, right? And the fact is that after they go to uni, every time they come home, they open the fridge, first thing they do, and if there's no milk, they go out to get some. So what's going to happen? Well, let's imagine roommate 1 comes home first. They open the fridge and they see there's no milk. Okay, so they're out at the shop getting milk. Next thing home is roommate 2 comes home, opens the fridge, there's no milk. So the obvious thing that happens is they've both gone to the shop. Maybe they've gone to a different shop to get milk. And then roommate 1 comes home with milk. And then the next thing that happens is roommate 2 comes home and we now have too much milk. So that's why it's the too much milk problem. So what are the solutions to the too much milk problem, intuitively? A couple of ideas for solutions. We could have a note on the fridge. So roommate 1 could have left a note saying, I've gone to get milk. And then roommate 2 knows not to check for milk until after roommate 1 gets back. We could have a lock on the fridge door. So roommate 1 goes to get milk. As soon as roommate 1 decides to leave to get milk, they close the padlock on the door and take the key. And then they go to the shop. And so they've got the key and the milk. And then they come back, put the milk in the fridge, unlock the padlock, and then it's available for roommate 2 to check if there's milk or not. The other option was maybe have 2 fridges. So the analogy has now gone too far. That was my fridge. It was my fridge from some time ago when it was neat. Not neat now. So we're not going to have 2 fridges, but these 2 options, a lock on the fridge door or a note on the fridge, are both good options, both good ideas. Talk about them in a minute. There's no such thing as too much milk. Imagine if there's only one milk space in the fridge. So if you're trying to add 2 milk bottles, the second milk bottle just falls on the floor and there's milk everywhere, which we obviously don't want. That's a huge mess. Yes, this is, I guess, a race condition. The definition of that is that there would be 2 programs running concurrently, being switched in or switched out, and we don't know what the output's going to be. So that would be, this situation is a race condition. We don't know what the output of these programs is going to be. This one is 2. We don't know what the outcome is going to be. So we have to find some way to make sure we do know what the outcome is going to be eventually. Okay, here's the technical term I want you to remember for this lecture. Mutual exclusion. The concept of mutual exclusion is a way of getting our computer to ensure that only one process can use a shared resource at a time. And we call the part of the program that's accessing the shared resource a critical section. So there might be a bunch of stuff that's using the fridge, all of that stuff is the critical section. As soon as roommate 1 opens the fridge, they're in the critical section. When they lock the door of the fridge and go to the shop, they're still in the critical section until they come back and unlock that fridge so that roommate 2 can enter. Someone said, isn't having 2 fridges similar to having 2 main programs? More similar to having entirely separate, not shared memory, actually. But we want shared memory. Okay, we've already done a lot of examples of what happens without. Let's figure out how we do it. Here's this is our simple program. We're going to do a for loop that counts things up and a for loop that counts things down at the same time, which is going to be a little bit tricky when we go into assembly. So both of these programs, these are 2 independent programs. These slides are courtesy of old friend of the course, Uwe Zimmer. So Uwe says, well, this one's going to load the count variable. It's going to put a 1 in my R1. Then we're going to count up to 100 and every time add those numbers to each of those indexes to our count accumulator. And this one's going to do the same thing, but it's going to subtract our count accumulator. Yeah, sorry for those who have got to go to another lab or a lecture. I'm going to keep going. We've got some, it's good stuff. I want to keep going through this and hopefully you catch up later. The important thing here is where we're doing the load and store in memory. The count variable here, that's our shared variable. So when we load from, as soon as we load from that variable, that's the critical section. Then we're adding 1, and then we're storing back to that variable, and we're exiting the critical section. So this area is critical. That's why we've got the yellow box around it. Same one here. We're subtracting 1 each time in that version of the program. What can we do about it in ARM assembly? Well, we've got a couple of special load and store commands called exclusive load and exclusive store. Now, I beg your indulgence, but the slide here is actually wrong. I don't know what Uwe was writing, but he wrote something that wasn't ARM v7m. It was a different ARM, or it was just ARM from his brain. We'll identify the differences later, but the idea here is sound. So as soon as you enter the critical section, as soon as we load that bit of memory, we're going to set some kind of tag to say I'm using memory. So this is the same as putting the note on the fridge. Note on fridge. And then we're adding R1 to 1 to R2, and then we're doing our exclusive store. Now, the exclusive store is going to only work if the note is still on the fridge. So roommate 1 gets back. If they still see their note on the fridge, they know no one has been in that fridge before them, so they can store back to the fridge. If they get back to the fridge and they see that their note is gone, then they know that there's someone else has been in the fridge and that they shouldn't be buying milk anyway. So they go back to the shop, return the milk, get their money back, and go back to see if the fridge is still is available again for milk checking. Oh, that's my R2D2 talking. So what we're going to do in this code is store or load from the fridge, have the exclusive tag set, do our work, add 1 to R2, and then store it back if it's untouched. If we find that our exclusive tag has been touched, we compare and branch if not 0 back to enter strx fail. Who can spot the issues with this code? I'll tell you what, CBNZ can't branch backwards. That's the first issue. Second issue is strx doesn't look like that. You've got to have another maybe R3 in there. you have another register in there to store the outcome. And the outcome of stirx is going to be, did the store occur or not? So you're telling it to try to store back to memory, and if it finds that it can't do it, it returns a 0. Or if it can't do it, it returns a 1. And if it can do it, it returns a 0, I believe. We'll find out in a minute with a demo. Same thing over here. Try to do an exclusive load, subtract 1 from the register, try to do an exclusive store back. This only works if we find that that bit of memory was untouched. And if it hasn't worked, we try to do it again. We keep trying to do this same operation over and over again until it works. So we keep opening the fridge, going up to the fridge, seeing if that note is there, and if it's gone, we go back to the shop. So we have to keep in this busy waiting loop, which is its own kind of badness, but at least it will solve the problem for us. So this means we will be able to complete these operations exclusively for each one. So here's the broad concept here. Whenever you've got two programs that have to have a mutual exclusion, they have to have a critical section that they ensure no one goes into, we work out who should go first, enter the critical section, and then indicate critical section is completed. So this is a pattern we're going to do in a few different ways. Another idea, we can have a kind of lock variable. This is putting the lock on the fridge. So we have this variable R3 called lock. The first thing we're going to do is to try to access our lock. If we find that the lock is not 0, then we try to access the lock again. So the lock is going to be 1 when the fridge is locked. Every time we see that lock is 1, we just keep trying again. We're waiting and waiting and waiting until the lock is 0. Once we find that the lock is 0, well, the first thing we need to do is change it to a 1. So we move R0 into 1 and then lock the door again. This is another time where we have to use the exclusive store, because there could be someone else's put the lock on the fridge just as we're preparing the padlock. We're moving it to the fridge door and someone gets in there before us and puts their lock on, and we then can't lock the fridge ourselves. So we have to try to lock the fridge, and then if we failed that again, we go back to here and keep waiting. There's this little operation, sometimes you'd have to do that in some systems to make sure that all of the memory loads and stores that are queued up have occurred, but we don't really have to worry about that today. Then in our critical section, we do our work. Notice we're not using letterx and stirx anymore because we've got the lock. We now have an assurance that it's our turn and no one is going to be interrupting our fridge work because the fridge is locked. After that, we get to unlock the value. We know that no one else is going to be messing with the lock variable at this stage, so we can use a regular store to store a 0 back in the lock. And that's our mutual exclusion in ARM v7m assembly, mostly. A few issues with these examples. What's good about this? The good thing here is that we have a small section that is dealing with our lock, and then we've got a critical section that doesn't have to worry about it. So the critical section, by the time we get to that stage, we know everything is fine. No one's going to interrupt me because we're all looking at this lock value. So this is mutual exclusion with a lock. What else is there out there in the big bad world? Well, this kind of exclusive store and exclusive load is not the only way of doing things, and you might see different options in different instruction set architectures. It comes under this banner of things called atomic operations. So an atomic operation is something that's defined to either happen completely or not at all. So it's an operation which is indivisible. This makes more sense in a higher level programming language because you might have some line of code, g equals g plus g, And as you know, this is going to boil down to about 5 lines of assembly code. Liturgy, G plus G, stir G, right, etc. So everything in assembly turns into more code. So we need to find ways to make our higher level stuff atomic. Another kind of operation you get sometimes is a special instruction that can read a value and set a new value atomically within the same instruction. So it's one instruction is going to load something from memory. It's going to load this value C, and then without allowing any other context switches to happen, it will define C to be 1. So we can use that. If we had that instruction in ARM, we could then use that to create our lock value, because we could be loading our lock from memory and setting it to be 1, and we only ever proceed if the value we get out of memory happens to be a 0. Every time we try to grab it, we keep setting it to be 1, but if we've grabbed a 1 and we set it to be 1, that's no big issue. It's only an issue when we grab a 0, we set it to be 1. That means we've now got the lock, and we can proceed to filling the fridge full of milk. Another option is this idea of an atomic instruction that can load a variable and then save or swap a variable with a local variable simultaneously, or within one atomic sequence. You can use this to do the same thing, atomic exchange. Same idea. And then the final idea is memory cell reservation. So we do some kind of way of reserving our place in memory. This is what we've got. Another word for it is load link / store conditional. This is what we've got in ARM. So when we load our variable from memory, we're in some way marking a location in memory or a region or the whole of memory as being exclusive, owned by us, or just owned, put a note on it. And then we can use that, as we saw, to accomplish our mutual exclusion. A more high-level version, and this is something you'll see in COMP2300, is the idea of a semaphore. So you might have a higher level variable similar to a lock, but it's going to be an integer rather than just a binary number. And that means that you could have a number of people waiting. You could have a shared variable that maybe only 3 people can use at the same time, or a shared resource, and use semaphores to accomplish something like that. We won't go any further into semaphores today. I just wanted to show you that there are higher level contexts possible. The thing to remember about concurrency is that this happens all the time. Concurrency is not an edge case. We always need it. So multitasking and multi-CPU systems have to have some kind of hardware support that gives you concurrency. And now you know how it works. So whenever you are, if you want to write an operating system for your microbit, it would have to use this exclusive load and exclusive store in order to make sure that different multitasking programs don't run over each other at the same time. Let's try it on a microbit. Finally, at the end of the lecture, we can do some demos. Sorry for those who had to leave. I hope you catch up later. What am I going to do? I'll make a label in memory, .data. You know, work word, and it's going to be a, oh, that's not how you do it. Work word, and that's going to be a word, which will be 0 or 1. I'll make it 1 to start with. Okay, and my main function is going to start with loading in this label. So we're going to see what happens here. It's a little bit hard to do an example here because I don't have a multitasking operating system, but I can show you how it works. If I want to load work word, I use the literx instruction, and now I've loaded in my 1 into my work word. Now let's just prove that it works. This is not going to be too complicated, too terribly complicated as a program. Loading in the address of work word, it's 20000 predictably, and then we load in our 1 into R1. No big deal. So what about this exclusive thing? Well, the way it works on your microbit, on Cortex M4s, is actually fairly simple. So when we do a letter X, we set what's called a local exclusive monitor to exclusive. That's a very simple thing. The local exclusive monitor is a 1-bit location, and setting it to exclusive just means setting that bit to be 1. So no matter what happens, we're now putting a note in that local exclusive monitor. It's like the fridge has a little exactly 1 note place, and we put a blank post-it note in that little spot when we go to the fridge. So now at this point, having read that data, now the local exclusive monitor 1 bit is set. So now when I come back and want to store something, I might want to change this value to 5. I'm now going to storx R2, R1, R0 and see what happens. Where is the local exclusive monitor in memory exactly? I don't know if it is in memory. I think maybe it's in either some kind of system register, or it's just like internally in the CPU and we can't access it. If I'm wrong and it's somewhere accessible, you can figure out and tell me. Let's run this program with storx. So storx is going to put R1 back in work word. So it's the semantic here is like fail, success, comma, register to store, comma, location. So R2 here is going to be an indication of whether we've been successful in our store. We've loaded our R1, got 1 out of there, moving a 5 into that, and I want to store it back. And R2 is 0, which means that it was successful. If R2 equals 0, success. If R2 equals 1, failure. Oh no. So we might want to do something to recover if we're in a failure system. We can compare R2 to 0 and BNE, try again. Try storing 5. Well, we're not going to branch to a second main program right now. It would be a bit too much for me to do today. I'm just trying to give you the idea of how these instructions work in ARM. We'll look at this again when we get to the operating systems lecture. So we've got a little bit of a week break for you to let the ideas settle in, and then we'll come back to it. And in your week 12 lab, you get to make 2 main programs. But what I'm going to tell you is we're going to do something to make sure that this fails. So at the moment it's succeeded. Would we always recover by trying again? You can do anything you want to do to recover, but in this case, I'm saying you should recover by trying again. There could be many things you would want to do. I'm giving you a fairly simple example, I guess. So I want you to imagine that in the middle of here an interrupt has occurred. Oh, by the way, why is it that storx is succeeding? So storx, what makes storx succeed? if Styrex finds the exclusive, if Styrex finds that the monitor is set to exclusive, then it succeeds. If Styrex finds monitor set to open, it fails. So Styrex is coming up to the fridge. It's got its milk in its hand. It's going to open the fridge door and put the milk in. But before it does that, it checks the local exclusive monitor, which you recall is a little space for exactly one blank post-it note, one bit of information. If the post-it note is gone, it knows that someone else has been here. And the question is, how do we know that? Well, if an interrupt occurs, an interrupt clears the exclusive monitor. So anytime an interrupt occurs, the CPU is saying, look folks, I know you had some exclusive work you were doing, but all bets are off now. Someone else has been in control. You don't get to assume exclusivity anymore. So it essentially runs this instruction. This means clear exclusive monitor. Interrupts always trigger a clearx. You don't have to write that in the handler, it's automatic. It's just something that happens. As soon as your interrupt occurs, the exclusive monitor is cleared. So if we have a context switch, we must have had an interrupt in between. That means that a clearx has happened. Let's see what happens with that clearx in between. Exclusively load R0, our work word. A clearx has happened. I don't know. It's changed an exclusive monitor somewhere. Let's see what happens with our store. Ooh, there's a 1 in R2. Try to compare R2 with 1, and we have to try again. And this will never work because I've got that clearx in the middle. And I can prove to you that it's not changed in memory. View memory, OX2, oh. Just want 4 bytes, and there's my 1. Should be a 5. If I get rid of the clearx, it'll work. Litterx, mov1 5, and stirx, there's my 5. I remember last time I did this, I showed everyone this information, and we got back next week, and someone was like, is it really just 1 bit? How is that going to work? So I'll let you think about it. Tao is there going to ask me about design documents again. R0 is the output of stirx. The question is, why are we comparing R0? So stirx is telling us whether it succeeded in storing the information or not. Has it succeeded in storing information, or has it failed to store the information? If it fails, we have to recover somehow. And R2 is being used to store the information about whether it has succeeded or failed. So if R2 is 0, it's succeeded. If R1 has failed, it fails. In this instance, I'm kind of faking it by putting in a clearx to clear the exclusive monitor. But in real life, we wouldn't have that there. In real life, we just have our program that looks like it's going to work until an interrupt occurs, and we don't know when those interrupts are going to happen. And whenever an interrupt occurs, the exclusive monitor is cleared. We might come back to this another time to try to get this knowledge sealed in, because it's tricky. There's a few more notes here. You can look in the reference menu about synchronization and semaphores to see what happens. In our case, if the address of stirx is not tagged exclusive on our CPU, store fails. Someone's just asked me, is it possible if we have two programs that both want to do an exclusive load and store, and they're both trying to recover by starting again, maybe they could be like blocking each other and end up in this loop of blocking each other. That can happen. It's called a deadlock. We don't want that. I'm not going to go into the different kinds of badness that can happen with synchronization. That's a COMP2300 topic, but yeah, there's bad live locks, deadlocks, starvation. I've forgotten the 5 bad things that can happen when you have got multiple programs. If you've got 3 programs or more programs, the badness gets amplified. So you have to have some quite tricky algorithms to make sure that badness is avoided. And one of them is this idea of kind of giving a ticket to someone, like a queue if you go to a butcher or a fish shop or something, they'll give you a ticket to serve you at the right time. So it's called the bakery algorithm, because it used to happen in bakeries. You get a ticket with your number on it. So there'd always be these queues happening. We don't have so many numbered tickets in Australia, but when I was living in Europe for a while, in Norway, every shop has numbered tickets. Like if you want to be served by a person at the electronics shop, you have to take a ticket. There's so many tickets all the time, and it took me a while to get used to that idea. But it does prevent people from waiting forever. I'll skip this stuff. We'll go back to it another time. Further reading about semaphores. If you want to learn how this stuff really works, have a look at this, Concurrent Programming and Mutual Exclusion. It's about Dijkstra's work in the 60s in the Encyclopedia of Algorithms. A really great article, which is really how I learned about this stuff. Have a look at these things. Now, making a millis function. This is a bit of an extra demo. I wanted to do something special and extra for you folks today for being so good and listening to me for 80 minutes so far. This will only take a few minutes, but the idea is there going to be a smarter way to measure time on your microbit than what we've been doing so far? And so far, a lot of the time when you want to measure time, you do some kind of delay function, which is just basically running a lot of nops, right? You're certainly measuring time, but it can be hard to measure it precisely. Is there a better way to do this? And we know now that you can use Systick to measure time precisely, but I'd like to suggest maybe a more general way, and this is something you might have seen before if you've done any programming on an Arduino or in a interactive programming system like P5 or processing. Because these systems they're usually for making different kinds of interactive systems where time is important. So blinking an LED on for a second and off means time is important to us. So you'll want to wait until a certain amount of time has gone by. And they give you a function called millis, and millis is a cool function which returns a value of how many milliseconds have occurred since your program started running. So how does it work? How does it work? I'm going to show you how it can work. Ooh, I may need to make this stuff smaller, but here's what we're going to do. Get rid of my literex and sturex. I don't need that right now. So my main function, whoops. I'm going to have my milliseconds count. I'm going to make a Systick handler. Systick. Is that yeah, underscore and a capital H. Handler. I don't want to mess up my Systick handler. I'm going to make a function called millis. So the millis function is simply going to return in R0 number of milliseconds since program started. And millis is going to be a very simple function. It's only going to load our liter R0 equals milliseconds count. I'll put in R1. and then letter R0, R1. That's it. Simple function. I'm going to need to do a few things here. It's not going to take me too long. First thing up here is set up Systick to fire at 1 millisecond intervals. All right, so far so good. Then the next thing down here is I'm going to make the Systick handler increment milliseconds count. That's easy too. We'll take this same data, load it up. Add R0, R01, and store it back. So now load milliseconds count, increment the milliseconds count, then store it back. So this is just a global variable. And it's the kind of thing you really will need to do more and more in this current assignment is use global variables to keep some track of state that are happening, particularly if you want some value to be accessible from your main program as well as a sys handler, an interrupt handler. It better be in some global variable stored in memory, because otherwise you can't really pass things to a handler, right? The handler just happens at any time, so there's no way to prepare for that handler to occur. So things need to be in memory. Okay, now the next bit is set up the Systick to fire at 1 millisecond intervals, and that's where I need my slides because I've forgotten how to do it. Ah yes, so I need to enable the Systick and then store a reload value. That's not so hard, is it? I could have remembered that eventually. I forgot. Whoop, enable my Systick. I hope I have my address syst CSR somewhere. Otherwise I'll have to enter that in manually. You've done this in your lab this week, if you've done the lab. If you haven't done the lab, you'll see how to use Systick pretty soon. Just going to set those variables because I don't think I have them in this template. OXE 000 E010 OX sets adra Systick RVR. There's probably people there who have a Friday lab or a Thursday lab who are really confused right now. So I guess I'm sorry to you. I'll explain how this works in a minute. You will do a lot of work in this in the lab in week 8 this week. What I'm doing is setting up a timer, and every time that timer runs out or sets its alarm, an interrupt occurs. And that timer is called Systick. And it's a timer which is built into the Cortex M4, and it's fairly easy to set it up. All we have to do is this, store 3 bits in the lower 3 bits of this memory address. That's the address of the Systick control and status register. The 3 bits there are enable the Systick, enable interrupt, and set the CPU as the clock for the Systick. So the way Systick works is that every time the CPU has 1 cycle, it gains 1 tick, basically. The next thing we do is, or it decrements 1 tick. The next thing we do is to tell it how long before in between interrupts, how many CPU cycles should go by in between a Systick interrupt. There we go, yeah, found it. The value I want to put here is the value that's going to make my Systick fire and interrupt every 1 millisecond, which is a very short amount of time, right? But my clock speed is very fast. The clock speed is, on the microbit, is 64 million cycles per second. So if I want to have 1,000 Systick interrupts per second, I just have to make it 64,000 cycles per interrupt. That gives me 1,000 interrupts per second, or 1 millisecond interrupts. So I'm setting the reload value, is what we call for Systick, to be 64,000. As soon as that starts, it starts counting down. When it gets to 0, after 1 millisecond, it will fire an interrupt. And then the next thing it does is just reloads that value back into the current value register of the Systick timer. So now I've set up my interrupt to give me these 64,000 clicks. Okay, now what? Every time that interrupt fires, it increments the milliseconds count. I've now got my function, which is going to tell me the number of milliseconds. So I guess I could use it. It's probably not going to do very much at this stage, because it'll still be 0, even if I have all these NOPs in. Set up the Systick timer, store a reload value in Systick, do a couple of NOPs, go into millis, load that value, it's still going to be 0, and return. I might need to have some kind of delay. Have I got a delay thing here? I don't have any of my libs. They're all gone. I'll write a really bad delay. Oops. Function, bad delay. It's going to be similar to the one that you will find in the utils folder, the utils file of your library folder. Bad delay function is going to count down a number in R0 and then return. So subs R0, 1, be my delay return, be delay, and delay return is going to be here. Very simple delay. So this one, it's difficult to measure time precisely with this one because each iteration is actually taking up 1, 2 cycles. So it's a bit unreliable. So perhaps I'll load up some big value into R0. Mov, loader, in fact, R0 equals, I don't know, 64 million or 20 million. We'll see how many milliseconds are 20 million bad delay iterations. 20, 1, 2, 3, 1, 2, 3. And then we will do BL minis. And then I will want to see what the state is here. So I'm going to put a NOP and put a breakpoint there. Uh-oh, something's wrong. What have I done? Always got some error, don't I? Undefined reference to delay. Whoops. Oh, B delay. It wasn't B delay, it was B bad delay. Like Bad Romance. That's an old song now. Load my large value into R0. I need my bad delay, I forgot. BL bad delay. Set up my timer. Now I could just click through my delay, but that's going to take a very long time. So I'm rather going to press play until we get to the end of that timer. I might have to compile this again. Hopefully nothing's gone wrong here. Oh, my... Doesn't seem to be working. Why is my code not working? I didn't try this pause. Where am I? Where have I ended up? In the default handler? What? What did I do? I'll step through it and see what's going on. Maybe I didn't set up my oh, I didn't .global Systick handler. .global. It's always something, isn't it? Always something. If you don't .global your Systick handler, as soon as that interrupt fires, it will go to the default handler, which doesn't do anything. Do we need comp before BMI? No, because I've got subs. That's going to set flags. Oh, it worked. Now we can load my milliseconds timer, and you can see that some time has gone by. 1,250 milliseconds proceeded. I mean, the debugger messes up time in all kinds of ways, so I'd never trust time when I'm using the debugger, but it seems like things were working. So I did succeed in having a milliseconds record in my program. The code for that is in the lecture. You're free to use this within your assignments. It's a good hint, a good trick for timing things. Some systems you might not want to have, or depending on what you're doing, you might not want to have a timer firing every 1 millisecond. Maybe more time would be fine for that. 10 milliseconds would be okay, but depends what you want to do. So with that, I don't think I have no other slides. I saw there's some questions lining up. I'll just reload and see if there's anything good. I was caught in a bad delay. Yeah, so the reason I didn't need to compare before the BMI was this subs will set the flag. So if it ends up with a negative number, it will set the negative flag, and then B- is just detecting if the negative flag is set. Luckily, I'm not caught in a bad delay. My bad delay always returns. You don't want to get caught in bad delays. Well, that was epic. What a day. We've gone through a lot today. I hope I boggled you a little bit. I will get back to this stuff in the operating systems week, so we'll have another chance to grok it. For those who are interested in the details here, please ask a question on Piazza. It's really fun to talk about this stuff. With that, I'll let you go back to your labs, other lectures, other tasks. Make sure you do the assignment pre-submission. I'll catch you folks on Monday.